I think the subject has been very well covered, and I would like to share with you just some of my experiences when it comes to control ventilation. Let me just pop this up. Okay, so bear with me just one moment. Okay, so Richard Beitmirza is my name. I have been working for Systemair now for a few years, and I will share with you some of the actual practical installations that we do today. Demand control ventilation has been around for a while, and this is a subject that can be like a layered cake. We can start at a very simple level and we can make it very complex, but we can simplify it for you. It's not so complicated. So it all starts with a demand. The end customer requires a demand, or the building is designed based on a demand. As our colleague said, this has to do with the activity. This has to do with energy savings. And based on these demands, we have to tailor what the ventilation that is required, heating, cooling, and the amount of fresh air that we bring in. There's two approaches to this. Either we will work with constant air volume, which consumes a lot of energy, and it will give spots where it's comfort and discomfort, or we can work tailored based on the demand and bring the ventilation optimized, really based on temperatures, quantity of air, quality of the air, on the activity and the need of the building. We've seen some comparisons up to today. What we tend to say is when we use constant air volume is the highest energy cost. When we go to VAVs, we're able to reduce that cost based on the demand. And when we use programs, controllers, where it is optimizing the use or the demand, we're able to reduce the energy cost below 50%. This will vary market by market. This will vary building by building. It all depends on the design of each building that is considered. Some of the benefits. So we know that as we reduce the pressure and maintain the volume, we're able to reduce the noise. Reducing the pressure also increases the energy savings. So this is almost a win-win. True initial costs are higher. We use a lot of AC fans, higher cost, higher energy savings. We use VAVs, higher cost, but higher the energy savings. So initial cost is always the issue, but life cycle cost and the benefits overweighs the investments that we have to do initially. The types of program available in the market varies supplier by supplier, and the approach varies supplier by supplier. So if we look at the general market view, what is important is that we see that rooms that are not used need to be minimum ventilated. In some countries, it should not be ventilated at all, but minimum ventilation is usually required in order to get rid of the odors and, let's say, stagnant air. Then there's a based on minimum use or maximum use. Here you see just a simple basic 2-person or meeting room cases. This is very typical. Things get a little bit more tricky once you have an open platform or multiple offices where you need to mix between constant demand or a constant load room or a variable room. Here is a very good example of how we try to save money, not only by bringing the right air into different zones, but also to try to extract in a collective way. What are some of the things that we have to be super careful when we use VAVs and demand control that I think is important. It is not only from the air handling unit to the chillers, but we have to go all the way down to the terminal devices. When we use a VAV and we go to the Vmin or the minimum ratio that we need to do, and we're still using delta T's that are higher than 6 or 7 degrees, we risk to have difficult air dumping. Basically what we have is we have the air that is cold or cooler than the room air, doesn't have enough speed, and this will drop. This is what is called dumping. It will bring a great deal of discomfort. So we have to design all the air terminal devices in a ratio that it is able to handle. And once we go to Vmax, then our catch is the sound level. So once we start going, the demand is low, we may drop the air. Once we go high, we may generate the sound. So it's extremely important which diffusers we use in which application in order to maintain the right speed on the face of the diffuser. These are just some examples and how we go about it. How far can we take this layered cake or demand control ventilation? This demand control ventilation can go to a great degree to control the valves, the room sensors, the extract, the condensation sensors, and so on and so on. And everything is controlled via a single room controller. So each room controller is the master of all the periphery that is around this unit. So if it is used with chill beams, you can control the water. If you're using chill beams, you can control the condensation sensor to make sure before you have any humidity or if you have any condensation, the valves get shut down automatically. You can control the air volume that goes into the room. So all this demand control ventilation is going to, let's say, the next step to be able to maintain a very good mix between different ratios. Here's another layer of how far we can take a demand control ventilation. In our air handling units, when we use an EC fan, we already gained a lot of energy savings. Also, it simplifies our life when it comes to 0 to 10 volt controls. So what we do is we drop a Modbus line that goes through every room, and you can go in series as many rooms as you want. Each room will have a number of periphery that can be controlled, whether it's valves, floor heating, radiators, beams, cooling, detectors, and so on. And that will give the signal back to your controller, and the controller will control everything that goes on in each room, room by room, sensor by sensor. In a small system, you can even control the average use of your heat pump. So it's not working based on outdoor temperature, but is working based on demand and the use, and it will continuously retake the average. And it can also control its number of series of water valves that is required for heating or other uses. So this demand control can be taken to a really high level if it's needed. Sometimes it gets tricky. Here I have an example of a project that I am working on right now in Sweden, where the consultant would like to use constant and variable load in the same building on open platform. In these cases, we have to work very precisely with pressure sensors in order to make sure that we maintain the right pressure and the right volume throughout the building, because it is one air handling unit for 2 floors, and it's different rooms and different requirements, and we have variable loads and constant loads. It is very easy to do, but it has to be done in a fashion that, we make sure that there is no errors in different loads. Here's another example I prepared for you. This is a very small school. We have roughly 4 air handling units, and within 4 air handling units, we have many different rooms. So in a scale of optimization, it is for what we consider quite small. Each air handling unit is managing, let's say, 2, 4, 6, 8 to 10 rooms, which double it for supply and return air. And these are basically working more with VOC sensors and CO2 sensors on extract air. So it's the extract air that is the master, it's the VAV on supply, which is the slave. And as the moment that the VOC or the CO2 sensor detects that 0 to 10 volt is going higher or the ppm is getting larger, we automatically increase the extract air, and the extract air detects that it needs to go based on the slave, which is the supply air, to give more air into the zone. So this can be taken in a very small scale to a very large scale. To share with you a large scale building, that's a building we did in Basel 2 years ago. This is a very interesting project because it's a LEED Gold building, and we have multiple layers here in a sense that we're doing shops, commercial, hotels, offices, all at the same time. And doing this, I think we had about 400 to 500 VAVs and different levels that was installed. It was a very prestigious building. So this can be taken to a very high level. And the complexity was that although this is an open platform, it is at the same time using VAVs per zone, and we are dividing it in 7 sections. So here you have a quick view of the controls that is inside the air handling units. We had 4 air handling units of 15,000 cubic meters. It's large size for Switzerland, but it's not so big. But at the same time, we used runaround coils in order to optimize the energy savings. And this was coupled with heat pumps based on CO2 to save even more energy and be eco-friendly. So we managed to do these on different levels in order to bring each floor and each zone control to a degree where the end customer was satisfied. Here's a quick view of the layout that the maintenance people look at. They basically see each room controller, and based on each floor and each room controller, they can click on it and they will go into the room and see different bases of the volume flow and the ppms that are coming in. And once they start going into different aspects of the requirements, they can tailor this a little bit higher or lower of what the customer needs are. This is what I have in short regarding demand control ventilation. So it is very simple and it's easy to do. It has some advantages. Using AC fans simplifies life. Using digital connections simplifies life. And after that, the building can be tailored in any way possible, up and down or left or right.